So the title of the presentation is Engineering Framework to Transfer the Lower Bound Fracture Toughness between half TSEB and 1 TCT specimens in the ductile to brittle transition temperature region. Here is the content of my talk. Predicting accurate test size dependency of fracture toughness of a material in the ductile to brittle transition temperature region, JC, is important in structural integrity assessment. Considering the large scatter and test specimen size effect of JC, it is important that the test specimen size effect of JC can be predicted from little test data and has collected interest from engineers and researchers. One of the widely accepted methods to bypass this test specimen size effect of JC is the master coverage. The approach assumes a statistical weakest model for cleavage fracture and uses variable distribution to express the scatter of fracture toughness KJC. The procedure is based on the concept that a normalized curve of the median fracture toughness for 1T, a 25 millimeter size thick specimen versus temperatures is applicable to a wide range of ferritic pressure vessel steels and structural steels. Thus, KJC median was expected to be expressed with a single parameter, the master reference temperature T0. Despite the efforts to apply the method, the approach is not without its limitations. For example, some results have presented that the master curve reference temperature obtained from SEB specimen and CT specimen show approximately 10 centigrade difference. We first sought to re-examine Chen et al.'s opinion that it is necessary to distinguish the minimum fracture toughness or the lower boundary values of toughness from that of the scatter band of toughness. The former is a definite parameter determined by the specimen geometry and tensile properties, and the latter is a statistical behavior determined by the distribution of the weakest constituent. We interpreted Chen et al.'s opinion as meaning that at least the lower bound JC might be predicted by running elastic plastic finite element analysis EPFBA with a given specimen relationship with a failure criterion. For the failure criterion, we considered one of the modified Ritchie-Rice failure criterion, that is the 4 times CTOD sigma 22C criterion, which predicts the onset of cleavage fracture when the crack opening stress sigma 22 measured at the distance from the crack tip equal to 4 times CTOD, a crack tip opening displacement delta T, exceeds a hereafter denoted as sigma 22D, exceeds a critical value sigma 22C. This criterion was validated as explaining the crack tip's dependence of JC by dot ZL and the test specimen thickness vector JC by S. Through the examination of the applicability of the 4 times CTOD sigma 22C criterion to the decommissioned reactor pressure vessel steel JC database with test specimen thicknesses ranging from 8 to 254 millimeter, we reached the idea that the convergence of sigma 22D is for increasing load is necessary for fracture initiation because fracture always occurred after sigma 22D reached sigma 22D. And in addition, the critical value sigma 22C is a converged value of sigma 22C at D. considering the fact that fracture always initiated after sigma 2 to d reached sigma 2 to c, we thought that the minimum j that could satisfy sigma 2 to d is equal to sigma 2 to c must correspond to the lower bound fracture toughness for the specimen and the material considered. Given these observations, we thought that the lower bound fracture toughness for different specimen types and thicknesses can be predicted by predicting the minimum j that could satisfy sigma 2 to d is equal to sigma 2 to c by calculating EPFEA with a given stress-strain relationship. Thus, the objective of this work was set to validate the proposed framework to transfer lower bound JC between different specimen types and thicknesses. Given that the room temperature tensile to yield stress ratio of the Euro RPBs and Japanese RPBs is 1.3, 0.55% carbon steel GIS S55C, whose room temperature stress ratio is known to show a higher value of 1.8, was selected for examination and tested at 20 centigrade. The sharp impact test results and tensile test results are shown in these figures. FTSCB and 1TCT specimen were examined. The details of the EPFEA are summarized on this page. The FEAJ, designated as JFEA, was evaluated by using the load versus crack mouth opening displacement diagram for SCB specimen and load versus low line displacement diagrams for CT specimen based on ASTM E1921. CTOD was measured at node A. After confirming that the linear portion of the load versus displacement diagrams showed good agreement with the relationships described in ASTM E1820, the relationship between sigma 2 to d, the crack opening stress sigma 2 to measured at the distance from the crack equal to 4 times CTOD at the specimen midplane, and JFEA was summarized in these figures. For both specimen types, sigma 2 to d showed converging tendency for increasing load as expected. Considering the fact that fracture always occurred after sigma 2 to d reached sigma 2 to c, we thought that the minimum j that could satisfy sigma 2 to d is equal to sigma 2 to c, hereafter denoted as JS, would predict the lower bound fracture toughness for the specified specimen at the specific temperature. Since there is not a definite method to determine the converged value of sigma 2 to d, here we applied the following method. First, the data set of sigma 2 to d and JFEA was fitted with a function shown here. Then, j at the value of normalized sigma 2 to d over the converged value of alpha 1 plus alpha 2 is equal to 0.95 was defined as the JS, the predicted lower bound fracture toughness. By using this method, the predicted values of JS was obtained as 9.3 and 3.5 Newton per millimeter for these specimen types respectively. For both the tendency that the predicted JS is higher than that obtained for half TSCB specimen is higher than that obtained from 1TCT specimen was observed as expected. Fracture toughness tests were conducted in accordance with ASTM E1921. The master curve reference temperature T0 for 1 TCT specimen was obtained as 24.2 centigrade. The test results were compared with the predicted JSs together with the master curve 2% tolerance bound values for half T and 1 T specimens. We see from this figure that the predicted JSs were sufficiently conservative compared with the experimental results and close to the 2% tolerance bound values. Though there might be an opinion that the 2% tolerance bound values are still not the lower bound values in a strict sense, it seems that the predicted JSs gives a good estimate of the lower bound JC in a practical sense. Thus, we concluded that the proposed framework has a possibility to transfer the lower bound JC between different specimen types and thicknesses in an engineering sense. The presented success in the current work indicates that the lower bound JC for a given specimen and temperature can be predicted with one kind of experimental data. In the former presentation, I said only one experimental data, but it's my poor English. If we use different temperatures, we need different tensile test properties for different temperatures. But the kind of experimental data we need is the stress strain curve. And the second, the lower bound JCs can be transferred between different temperatures. And this was presented in another work at this conference. Next page. Next page. Despite the presented success,
we need the page.
So,
next page.
Okay. So, despite the presented success, we acknowledge the needs of some future works to be done before finalizing the proposed framework. We are aware that a threshold value of 0.95 for the FEA modeling will affect the proposed predicted JSs, and are working on a way to finalize and standardize this issue. And besides this numerical procedure, we are also aware that we have to clarify the physical meaning of the predicted JSs, though this is an engineering approach. Sorry for that.
Okay. This is not here. So, conclusions. This.
Next.
So you are moving. This.
So I think the problem is fixed. function is back. Some rough side evidence we recognize is that the predicted JS seems to correspond to the turning point of the load versus load line displacement diagram. That is, if fracture is to occur at this load, then no plastic deformation is observed before cleavage fracture. Because we are considering elastic plastic fracture toughness JC, this finding seems to give some idea of the lower bound JC in a practical sense. The success of the Masakov approach based on 1D CT specimen seemed to support this finding. So sorry for your inconvenience, and this is the conclusions of my talk.